Claire will be presenting two projects. Rocq and Roll, which is a tool for sonifying the tactics of the Rocq proof assistant, which is based on dependent types, and Prismriver, which formalizes rules of counterpoint in the proof assistant Lean.
Okay, so this talk is on two projects related to connecting music with proofs and dependent types. These are kind of like the leading questions I had before doing anything. I was kind of curious, like there's structure in hearing Baroque music, like maybe there's similar relationships that we can formalize between like math and music or whatnot. And ultimately I realized, like the common bread or glue that I can use to explore this is through computers, through programming languages. And just like as a preliminary, just like in Isadora's talk, she briefly discussed how this whole idea of propositions correspond to types in the Curry-Hauer correspondence. So basically it's like for each logic proposition, you can have a type, corresponding type in a programming language. And dependent types, you don't have to know this. This honestly took me years to understand, but basically like it's a way to be able to pass in to parameterize values in your type construction. And yeah, I'm not gonna go too into it. We don't have to. So the first project is based off of the Rocq proof assistant. So this is back to, I briefly mentioned dependent types, but basically think of proof assistant as something like a programming language, except you are able to express proofs in your programs, and when you type check your proofs, it's able to actually check if your proof was actually proved. So Rocq is a widely used proof assistant, also can be used as a programming language. And I can even show you guys an example of how to use this. It ends up becoming like really interactive. Like just think of it like an existing, like a REPL that you can like write proofs in instead of just programs. So right here, I have VS Code with like a really simple Rocq proof. And it tells you like your goal. So given this theorem that you want to prove, which is like for any n, you add 0 to n, you get n. So it tells you like, it provides you your goals, and then you can use these things called tactics. So kind of like using keywords in a language. When you apply each of these tactics, there's a bunch of them. You don't have to understand this entirely, but the idea is that the Rocq proof assistant has a bunch of these tactics that you can use to transform your proof state. And then as you apply these tactics, it shows you what you have to prove next and the result of using them. So you don't have to understand this entirely, but just giving context on this is a thing, and I recommend that you learn this at home. You don't need to know any math to use the Rocq proof assistant. So that proof I just showed you, I was curious, like, what could this maybe sound like? And that led to creating this little tool called Rocq and Roll, joint work with my colleague, Roger Burton Patel, where we literally just take an existing Rocq proof. So one thing we were curious about was, what does verified LLVM sound like? So we take like an existing proof, and then we want to hear what it's like. And so how does that design exactly work? What we decide to do is we take an existing proof, we parse it, and in case you want to, like, in general, sonify any language, I think it's super useful to use the language server protocol, because that's a way to programmatically take a program, and then given the language, you can basically talk to the compiler, interpreter, and have it respond to, this is like the response, or this is the result of the program of your code. So we basically used a MIDI protocol and the language server protocol. Language server protocol we use to interpret the program, get like the result of it. Then we take the result of the program and then we map it to MIDI pitch velocity pairs. Then we send it as MIDI messages, and then those are sent to a synthesizer or, yeah. So that's kind of how it works. This might be like a little bit too much information, but we also were curious about, so I showed you those tactics earlier. The tactics can be used kind of like they can be used like programs. So in one example, you could have a tactic that you use in a proof, and maybe like the result is multiple things to prove in your proof. And so sometimes like we were curious, like if we use like a, how do I say it? Basically, if we use what they call a tactical, where you could just apply a bunch of tactics to a proof at once to all of its subgoals, what would that sound like? Maybe that can sound like a chord. Another thing is there is a tactic called auto, which will apply a bunch of tactics to a proof under the hood. So we were curious, like it would be cool if we could hear each of the individual tactics when auto is called. And then, yeah, this is basically like the overall architecture or flow of how the tool works. And if you're interested in like collaborating or discussing more, you can reach out to Roger Burton Patel at this email. And I'm gonna show you a really quick demo. It's not gonna be a performance. So in this proof, I mentioned like you can have something called like a tactical, where if you apply a tactic, you might get multiple goals to prove. Then you can like specify, like apply this tactic to all of these subgoals that were just created. That will be like multiple proofs at once. So we wanted to hear what does that sound like all at once? And that way, that becomes like a chord. I don't know if that makes sense. I'm happy to clarify afterwards. And then next one is a theorem where we just use the auto tactic. So you'll notice there's really nothing there, just auto. So after the QED, auto is sent to the language server, and then now we can hear like 2 notes or whatnot. And supposedly that maps to the tactics that were used under the hood when auto was called. And also, I want to point out, for each of these tactics, we actually had to hard code pitch velocity pairs in MIDI. But when we go through the proof, given the proof state, we slightly distort the pitch and velocity. So that way it's a little bit more interactive and responsive to the given proof. So the next thing I'm going to go into is after trying to see, how do we sonify proofs, I was more curious in like how do we actually formalize music in our proof assistants. And so I showed you guys Rocq, but another popular proof assistant is Lean 4. I think it's been pretty hype recently because Terrence Tao uses it. But the value of Lean 4 is because it has MathLib, which is probably the largest library of already proven proofs that you can use if you want to reuse in whatever you're trying to prove. And so the greater goal was, like, if we can somehow have just like a base library to represent music, we can eventually import MathLib proofs, and then we can start to prove a lot of interesting things about music. And so the first thing we started out with, because music has a bunch of different systems, but the easiest thing was, okay, let's start out with an actual tangible end goal we can start proving. So we chose counterpoint, which is rules that guide in composing simultaneous musical lines. So in this, notice how there are two sorry, I'm not really a music person, but see these two lines, right? The fact that they're simultaneous, they're parallel, right? How do you know if that's going to sound good, like great, or if it's going to make sense? Counterpoint gives you the composition rules to guide that. So the cantus firmus is your starting musical line, and then the counterpoint would be the added simultaneous line, and there can be one or more simultaneous lines at the same time. And so we were curious, is there a way where, given a counterpoint, can we prove properties about how, is this counterpoint actually of first species counterpoint? And as you see here, there's like a bunch of different rules. So this means all of these somehow need to be represented in our in Lean somehow. So the first thing we started out was representing what a note is. And notice, I will say for now, I'm not going to mention time, but I will address that later. But with a note, we had to represent the note letter. So we used a heptatonic scale, note letter, and the octave. And the heptatonic scale, we used a note letter, so C, D, E, F, G, A, B. We have to map them to integers, and then basically these 7 consecutive letters, they make up an octave, and as you move up and down the keyboard, like the order, I guess like the structure still persisted, except it's like varying different offsets with, how do I say this? It's like different parts of the keyboard that you move up and down with, if that makes sense. So every 70s octave, and we also used a modulo of 7 equivalence class to kind of represent, for this, when computing where exactly on the keyboard, we'll represent it with an integer, but we still have to account for the offset or to account for every new octave that we run into. So this was very useful. It fit in nicely with figuring out, given this pitch, where on the keyboard are we? Sorry if I butchered that, but also if anyone knows more music theory, feel free to interrupt. And then, we also had to represent semitones and accidentals. And I guess what was really nice is how all of these can be integers or natural numbers. And then here's an example of a proof using our existing, in this case, we also, I'll link our repository later, but we built up a couple of representations, notes to scale, semitones, and accidentals, but basically what I'm trying to say is this would be how someone would prove stuff about music using our library. And so now, for counterpoint, there's a lot of rules that kind of calculate, this cantus and this counterpoint are consonant if there's if your interval, difference in pitch between two sounds, if your interval fits some kind of range or whatnot. So we had to find a way to calculate intervals. And one interesting thing, this is more of a quirk of the language. We got to use group actions to calculate the distances between pitches, because the way that we represented our interval had both the pitch name, right, the semitones and the pitch name. So basically, in order to add or subtract between heterogeneous types, you can use that with group actions in Lean. And so finally, so first species counterpoint, you don't really have to worry about rhythmic variety, but counterpoint has these different species, which I think of as levels. And as you go up the species, the counterpoint gets more complicated. So if we want to be able to create counterpoint more complex than first species, like second species forwards, we need to actually know rhythmic variety. So that's when you think of a note, that could be also a quarter note or a half note along with the pitch. So the way that we wanted to represent time, since we also we have our existing system of integers and naturals, but we also want to be able to divide things up. Well, one really easy way is to just start using rationals. So that was pretty interesting too. And then we also, and now that we have time, we can also represent time signatures and bars, and those bars can also compose up to entire pieces. And then we also keep track of duration, right? So because we have time now, we also have the duration of each note, but then for each individual note, given its bar and time signature, it must also, we also need to keep track of the global time. So the global time signature would be, given your bar and time signature, this is the total amount of time in it. And then for each of the notes in the bar, we have its duration. So basically, what I'm trying to say is you need to keep track of both each individual note's duration and the time signature in the bar that it's in. And then I mentioned, like, in second species, you start to have to care about time. So in the second species counterpoint, basically for every note in your cantus, your counterpoint needs to have 2 notes that correspond to the cantus's duration. And so this is like a proof that kind of asserts, oh, like, give me the cantus music line, the counterpoint music line, and for each of them, make sure that the corresponding counterpoint has half the duration of the cantus. And then these are our next directions. We want to be able to transcribe Lillipont and Music XML automatically to our representation to start immediately writing proofs about it. We also want to compose music with Lean and also implement other music systems. So if you're interested in working with us or have any feedback, feel free to reach out. And then these are the QR codes for both the repositories I mentioned. We have thought about that for specifically Toho music, so stay tuned. Like Toho, the game. It's honestly super basic, but things like, oh, like if this tactic applied to this proof ended up suddenly increasing the amount of goals I have to prove, I guess, like, anecdotally, that's usually a bad sign that I haven't done something good to my proof sometimes. And so given that, right, we would like distort it and make the music more negative, but really basic things like that. Wait, so is it like figuring out when it goes back to, sorry, say that. Okay. We are actually working on formalizing chords right now. I didn't have that prepared, but I would still be using the existing intervals and semitones representation and just see if that would work. Wait, what? Oh, I did a demo earlier, but I can show you. Oh, right, yeah. it would just sound really long. Like you could just like step through it.
There was a performance of a large proof that Claire did with Roger at the farm workshop, which the recording of the performance is not like up yet, but at some point should be. So we would probably post that on our Instagram, but that may be in months. I don't know exactly when.
Okay. Sorry if you mentioned it and I missed it, but how did you decide on the pitches for the tactics?
So for Rocq, that's all hard coded. Yeah.
Do you use your whole system you've invented to put music to other things, like a chess game? So a different chess game can make different songs depending upon how boring or interesting it is.
I think that would be possible. Maybe you just add like some intermediate representation in between and convert. Yeah, I don't know about that, but possible. Huh?
So you said you did things using like a 7-tonal system, like especially like trying to change between keys. Is it sort of? I guess I would just naturally think that like what you would think to do is like some sort of like 12-tonal thing, and then you see like individual keys occupying some 7 tones within that 12-tonal system. I guess did you think about doing it that way?
I think it just seemed easiest to just do the system of you have your starting pitch, and then you also have how do I say it? Let me get back to you later. Actually, yeah, sorry.
Question on the actual like proof structure itself. What for someone not familiar with like the calculus, how does one translate like an easier proof, let's say, what is it, the Pythagorean theorem into these systems? Like a more simply understood way.
Like, are you asking how to write this in Rocq itself, or are you asking like how to express this also with a music representation? Or if you just look up Pythagorean theorem, Rocq, or lean, you'll see something. Yeah.
The idea is that you have the Euclidean axioms that talk about there's these relations between points and lines and so on, and then you can derive this stuff from those axioms. It fits into the system.
So I'm just curious, what's your own backgrounds? Were you writing a lot of rock and became interested in music, or how that came about?
I'm just like a first year PhD student, but like before that, I had not much of a math or music background still. So
Yes.
What are the axioms for music proofs?
oh, if you look at the QR code that I posted before, I can also give it to you later. We have a couple of different axioms you can reuse. Yeah, but there's a couple. Sorry, that's big.
So is the conversion to audio done on the proof script, not the proof term?
So for
Rock and roll.
okay,
Is it done on the tactic, proof script, or the term?
I would say like each line that you step in through the proof, and then that's tactics. Yeah.
Because like you could have the same set of tactics, but depending on the context, the proof term is going to be quite different. So did you consider doing converting the proof term to audio?
Converting the proof term.
Like when you press QED, it constructs the proof term that represents the fitness of the proof. So you could convert that entire term to so you might like if you do like intro or something, it's going to do different things depending on like what you're proving. Or if you do rewrite, it may rewrite several places in your proof. So yeah, you might get like a more consistent audio if you operate those proof terms.
Okay. I don't think we do that, but I'll look into it.
That's kind of what I do in my piece.
Okay. Yeah.